Hello and welcome to this seminar on working with multi-hull designs in Maxsurf. I'd like to give you a brief overview of the topics we'll be covering in this seminar. First of all, we'll be looking at generating the surface model, looking at symmetry, asymmetry, bonding and trimming of surfaces, as well as setting up the reference frame and defining the vessel type. We'll also look at performance prediction, that is calm water resistance, and motions in a seaway. We'll look at hydrostatics and stability, as well as the definition of primary hull structure. So what are multi-hulls? Well, this covers a wide range of vessels, including catamarans, SWATH vessels, semi-submersibles, trimarans, proas, and also vessels in proximity, such as a fleet of vessels travelling together. Now I'd like to look at modelling the symmetrical submerged part of the hull. Often for a catamaran, the demi-hulls are symmetrical about the centre line, and we can simplify the model by modelling a single demi-hull on the centre line. This can then be used for hydrostatics and motions analysis. Okay, so now we'll look at modelling the demi-hull on the centre line. So we can start by adding a surface. I just use the default surface, which is just a fairly simple cylinder. This is just really to give an idea of what's happening. As you can see in the body plan view, here's the centre line. So we've got a symmetrical surface that's mirrored about the centre line. So the next thing to do is to make this look a little bit more like a vessel, give it a pointed bow. So what we can do here is either drag or change the value of the control points. We can do this numerically or by dragging it. So if I double click on there, I get the position of the control point. So at the moment it's longitudinal position 10 meters. What I want to do is basically move it forward and put it on the centre line. So I'll put 12 meters for the longitudinal position and an offset of 0. You can see the hull is starting to close. And then this point here again needs to go on the centre line, so I'll do that. So offset of 0, and I'll make it a little bit further forward. So we've got some rake in the bow, so I'll put it at 13. And now we have something that looks very vaguely like a vessel. Okay, so now we can size the surface to match the requirements of the vessel. So if we go to the surfaces menu, we have size surfaces. By default, this surface is selected. We can set the length, beam and depth independently, or we can fix them in a ratio, but now we want to do this independently, so I'll make it 40 meters long. Remember, this is the beam of the demi-hull, so I'm actually going to make this maybe 5 meter beam, and this is just the underwater part, so I'll probably leave this, maybe just reduce that a little bit to maybe 3 meters. Okay. So now you can see we've got a much more longer and slender vessel here, slender hull. What I can do now is, because it's quite tapered near the bow, I can add some more parallel mid-body by adding a few more control points. So if I go to the plan view, so what I want to do is add some control points and then slide these ones forward. So what I do here is go to the add control points command, and this will put another row of control points here that give me a bit more control over the shape. So now if I turn on all the control points, I can just pick them up and drag them forward. So as I mentioned, this is a very simple model of the lower part of the hull form. What I need to do now, obviously you can make this a lot more complex if you want to, and we'll look at some examples of that in a moment. But what I want to do now is just check the hydrostatics. So before I can do that, I need to set up the frame of reference so it's at the correct water line and the perpendiculars are correct. So it's in the data menu, and I've got frame of reference. So this dialog here is used to set up the frame of reference. So what I would like to do is find the lowest part of the hull, find the baseline. So I can click on this, find the baseline. And I want to use that as my vertical datum, so I'll click that there. So this slightly paler representation is the way the new 0 point will be. And then I want the aft position to be at the transom, so I can set the longitudinal datum to be the aft perpendicular, but I need to set that aft perpendicular to be the aftmost point on the vessel. And you'll see here actually the DWL here is just at this point here, so that's I can actually lower that a little bit, so I'll make that minus 0.25 for instance. You can see that's a little bit lower. So now with this set to DWL, that will automatically see where the model intersects the waterline. So it's minus 17.319 meters. And I can do the same with the forward perpendicular. So now these radio buttons choose which points will be the longitudinal and vertical datum, and the zero, so which means 0 point will be here. So now I can check my hydrostatics. So if I go to the data menu, do calculate hydrostatics, and this will give me a range of hydrostatics like the volume. Obviously for the catamaran, the displacement would be twice this, and the transverse stability obviously would be quite different because the hull would be offset. So what I'll do is save this model. Okay, so here I've loaded the model into Maxsurf Motions, and what I want to show you here is how we can use just a simple model of the single demi-hull, but look at the effect of demi-hull separation on the roll response. So what I need to do is, first of all, I've measured the hull already, so I've done a number of sections, and you can see the conformal mappings here. I've defined a spectrum, a heading, and I can put the speed in, so say 12 knots. And at the moment it's in a single demi-hull configuration, so I could analyze that. What I can do also here is in the vessel type, I can make it a catamaran and make the spacing say 10 meters. You can see here it's very easy without having to actually modify the surface model. I can generate the motions for different hull spacings and look at how that varies. So here I've calculated the motions for this particular catamaran configuration with a 10 meter spacing. So I can very easily change that spacing and look at the variation. Here we've got the REOs and beam Cs, and here an animation of the vessel moving in the irregular sea state that we specified. Here some results for different spacings, so not quite the same catamaran but different spacings, 18, 12, 26, 31 and 36 meters, and you can see how the REOs change actually quite dramatically depending on how the interaction that you get between the two demi-hulls. So with the closer spacing there's quite two strong interaction points here, which decrease and then increase again, as you see here. 36 meters is twice 18, so we're getting that same sort of resonance between the two demi-hulls, but at a slightly lower level. Okay, so that was a very simple sample that I showed you just now. Of course, anything that you can do with a monohull, you can incorporate into a catamaran demi-hull. So here's a few other examples I've generated. So it's a longer, slender hull, but again similar form. Here we have a multi-chine demi-hull, sort of planing type catamaran. Of course you can add bulbous bows and all sorts of other features. And here's something that could be used to generate a SWATH model. We'll now look at modelling the complete underwater part of the vessel, and a similar approach is used for both catamarans and trimarans, involving mirroring and duplicating surfaces. We'll look at defining the vessel type, as well as defining the locations of the buttock planes. The next step in generating the catamaran model is to move the demi-hull from the vessel centerline to the centerline of the demi-hull. So we're going to move the surface transversely 7.5 meters. We'll also rename the surface to hull outer. And now we'll make a duplicate of this surface, but a mirror image about the local demi-hull centerline, which is again 7.5 meters. Now we have something that looks a little bit like a catamaran. The next stage is to set up the vessel type, so this is in the data menu. We can specify that it's a catamaran and that the demi-hull centerline offset is 7.5 meters. We'll also rename the surface. So we can now set up the design grid that specifies the planes that are used to generate the sections, buttocks and waterline contours. So we can add, say, 21 stations. We can space those evenly along the length of the model. We can add some buttocks. So because it's symmetrical hull about an offset of 7.5 meters, we could do maybe 3 buttocks. And we can put in a start. And again, we can use the space command. This time we can specify a step. And specify some waterlines. We'll do them through the depth of the model that we've got defined. Now if we turn on the contours, you can get a better idea of the shape of our vessel. Of course, there's nothing to stop you making the vessel asymmetrical, or the demi-hulls asymmetrical. It does, however, mean that it will be less accurately modelled in the resistance and the seakeeping package, apart from, in fact, the panel method. So a simple way we could do that is just pick up those control points and move them in a little bit. And you can see now we have a catamaran that's slightly asymmetric. Should we want to maintain symmetry, however, the simplest way is to use XL to mirror the control point locations across the demi-hull centerline. Now at this point we could actually do some analysis of the resistance, so let me bring up the model here. And because we've specified a catamaran, the Slender body method automatically generates the mesh for the 2 demi-hulls. We'll now generate the upper part of the vessel, which will join the 2 demi-hulls together. We'll look at bonding surfaces with a catamaran example, and trimming surfaces with a trimaran example. We'll look at fairing surfaces over bonded edges using the align to vector command, and also the different bonding conditions that are available. We'll look at surface-surface trimming and defining the cutting surfaces, which are useful for complex models with many surfaces. I'll now look at one approach to generating the topsides and bridging structure of this catamaran. We're going to use bonding surfaces. So for bonding surfaces, I need surfaces with the same number of control points and the same flexibility along the edge. So the easiest way to generate that is in fact to duplicate the surface. So I'll just do the outer hull to start off with. And what I can do now is bond the 2 together. So what I'll do is organise my surfaces here so I know what's going on. So to bond select the edge, I have to turn the rendering off. So the first edge that's selected is the one that remains stationary, and the second edge is the one that will bond to it. And I've got this bonding command here, so at the moment I'm going to use just position continuity, no tangent continuity. You can see that forms a bit of the top sides. Now if I want this bow to be nice and straight, I can use the align to vector command. If I choose these 2 control points to define the vector, I can then choose these 2 control points to be on that vector. And if I hold down the shift key while I choose align to vector, I get the option to constrain the points to the height that they're at. Just going to change the surface color to make it easier to distinguish the different surfaces, and also I can turn on the display of the bonded edges so I can see those more clearly. So the next stage is to duplicate the inner part of the lower hull and use that to form the tunnel. So as we did before, duplicate surface, but here I want the inner hull. I'll turn off respect bonding because I only want that surface. And again, I want to bond that new surface to the top of the inner hull. So again, select the two surfaces and bond. So now again I'm going to name the surface, so this and put it into the correct part of the model. So this is the tunnel. I don't want to change my lower part of the hull anymore, so I'm going to lock that. I also want to lock the outer top sides and just concentrate on forming the tunnel. So that's easiest done in the body plan view. And what I'm going to do is basically bring these points down to form an arch. And I can put them all at the same height as this one, which is 5 meters. And now you can see we've got something that is approaching a catamaran. So now we'll add a surface that will join this to the center line here, this tunnel to the center line. And again, we can duplicate the surface when we use that tunnel as a basis. So surface, duplicate surface. So we're going to make a turn off respect bonding, just want the tunnel. So again, we can bond the surfaces. And at this point here, it starts to get a little bit complicated, but if we go to the body plan view, we can see a bit more what's going on. So in fact, I wanted just a flat surface here, and which means I don't need these control points here, so I can delete those. And all these control points here, I want them to be at a height of 5 meters and an offset of 0. So there you can get some idea of a quite simple way of closing the model, the demi-hulls, and getting somewhere towards a catamaran. Now look at a method of closing the forward part of the hull. Again, I use bonding surfaces, and I've generated a couple of surfaces here that we can use to do this. So first of all, I'll just turn the rendering off so I can select the surface edges, and to simplify what's displayed, I'll just show half. So this is going to be near the bow. This is the bow plate, and then this other surface is the bow curve, which will fill in this curved gap here. So if we bond these two together first, then we can bond that to the tunnel bottom. Now I have to unlock these two surfaces, otherwise the bonding will cause problems, so let me just unlock all of that. So now remembering that the edge that I select first is the one that doesn't move, so I select the tunnel edge and this one, bond that in, and then finally just bonding to the bow here. So that completes a fairly simple catamaran. But now I'd like to show you a bit about trimming, and this is with a trimaran sample. So I've used trimming here instead of bonding to get these to join into the main part of the hull, which is bonded together. I used trimming because they're quite a lot shorter than the actual vessel length, and trimming seemed one of the best ways of doing this. So you can see here the surfaces intersect, and we've used trimming. You can see here that this surface here pokes through the bottom, the tunnel bottom, and in fact is trimmed off. So though this model is quite simple, it can be useful to choose which surfaces are used as cutting surfaces. This surface here is the armour inner, and it's being trimmed against this surface here, which is the main hull upper. So if I select the armour inner, I get a list down at the bottom. I've got a list of the cutting surfaces. So if I select cutting surfaces, I can see that I'm just using the main hull upper and the transom as cutting surfaces. So this greatly simplifies trimming with models with many surfaces. It's well worth using. When looking at calm water resistance, it's normal to break down the resistance into different components which scale as Reynolds number or Froude number. So here we have CT, total resistance coefficient, is the sum of the wave pattern resistance, CWP, which scales as Froude number, and CV, the viscous component, which scales as Reynolds number. Now CV can also be defined as 1 plus K, which is the form factor, multiplied by the skin friction CF of a flat plate, or the ITTC 57 ship model correlation line. In the Maxsurf resistance program, we have several regression methods available, but these are for monohulls only. We also have the Slender body analytical method, which can be used to calculate the resistance of single and multi-body vessels. However, each body must be symmetrical about its local center line. The method is inviscid, i.e. viscosity is ignored, and can be used to calculate the wave pattern resistance, CWP, and the far-field wake pattern. Looking at the Slender body method in more detail, the flow is modelled by an array of sources on the center plane of the individual hulls. This requires that the hulls are locally symmetrical, and the analysis mesh is calculated from the starboard side of the vessel only. This enables the wave pattern resistance to be calculated, as well as the wave wake pattern. So now I'm just going to show you how you can calculate the calm water resistance using the resistance program. So for a multi-hull, the only method we have available is the analytical method, the Slender body method. And that can be selected from the methods at the bottom here. It's also necessary to choose the form factor that should be applied to the ITTC 57 skin friction line. And there is a method proposed by Molland, and that depends on the slenderness and separation of the demi-hulls. Or you can modify the value or type your own, so we could maybe have 1.3. The next thing to do is to verify the Slender body mesh that's used to calculate the resistance. And this can be displayed by turning on this button here. And if the vessel is set up correctly as a catamaran, with the demi-hull centerline correctly positioned, the mesh should come out correctly. If this is not the case, you can modify the definition of the Slender body mesh using this dialog here. And this can also be used if you're looking at more complex vessels where you require more than one mesh. Here we only need one mesh on the demi-hull, and it's symmetrical. So the main idea is to select the surfaces that make up the demi-hull and that should be used to generate the mesh. So we've selected them all, and that's fine. In this case, it's not really necessary to have the cabin, but that's not really a problem as it's above the water. We can also specify the fore and aft limits and the port and starboard limits, as well as top and bottom. But these are normally generated from the selected surfaces. But maybe most important is the transverse Y offset. So if that was 0, you'll notice here that the mesh goes back to 0 here, the center line, which is obviously incorrect. So if you get something like this, it's because your model hasn't been set up correctly as a catamaran. So now what remains is to set the range of speeds. And because the calculation takes a few seconds, you have to actually run the calculation. With the regression methods, they solve instantaneously. So there's the resistance calculated. We can see the graph here. Now sometimes with these sort of multi-hulls, it can overestimate the interaction of the wave pattern. So in practice you probably wouldn't get this reduction in resistance at this particular speed. You can also look at the different resistance coefficients. So we can look at the wave resistance coefficient, which is basically the part that's calculated by the Slender body method, as well as the viscous resistance coefficient, which is the skin friction line multiplied by the form factor. We can also calculate the wave pattern. This is a lot more time consuming because every point on the wave grid requires the same amount of computation as one speed, and so often you have a wave grid of maybe a few thousand points, so obviously it's a lot slower. So basically we can choose the speed we want to calculate at. If the vessel is symmetrical, we can just calculate over half of the wave domain by turning on this mirror, and basically we can specify, if you imagine the vessel here, the number of ship lengths aft, forward, starboard, the number of points to use transversely and longitudinally, and then this is the precision factor which is used in the numerical integration. The larger the number, the more accurate the results. So here's the calculated wave pattern that's been calculated by the Slender body method. There's various ways of presenting this with ISO contours or just shading of the wave pattern, and smooth shading with and without the grid. Because the wave pattern takes such a long time to calculate, it's possible to save it, so you can save the free surface as a file, and it's possible to reopen that. It's actually a plain text file, so you can do wave cuts along any one of these grid points if you wished. The ship motions that we'll be considering are linear and in the frequency domain, which allows the principle of superposition to be used. We'll see how the response amplitude operators of the vessel are calculated, and how these can be combined with idealized wave spectra such as John Swap, Brett Schneider, ITTC, etc., which allow statistical measures to be computed and used as a tool to compare and assess the performance of different design alternatives. The performance assessment may include sickness incidents, crew performance such as motions-induced interruptions, as well as the calculations of accelerations or motions at different parts of the vessel. So once we've loaded the model into motions for hydrodynamic analysis and seakeeping analysis, we need to specify some parameters about the hull. The main one is the mass. So as well as specifying the vertical center of gravity, we also need to specify the gyradii in roll, pitch and yaw. And these can either be specified as a numerical value or a percentage of the beam length. The mass is automatically calculated from the displaced volume of the vessel. We can also specify the density of the seawater and the number of frequencies to be calculated. We also need to specify a range of speeds. You can give them a label if desired, and you can also, if you have a range defined, select which ones require analysis. Similarly for headings, we can specify a range of headings which should be analysed. You can also specify a number of sea spectra. There's a variety of different idealized wave spectra that may be chosen. And also we can look at different locations on the vessel for accelerations, seasickness incidents and other parameters. Looking at strip theory in more detail, the vessel is typically divided in 30 or 40 strips. Conformal mapping is used to solve the added mass and damping on each section, and this is integrated over the length of the vessel to obtain the global added mass and damping and wave excitation. The coupled heave and pitch motions can then be solved. However, for a catamaran, demi-hull interaction is ignored. Looking at the roll motion, for a monohull this is dominated by viscous damping, either due to skin friction or eddy generation from bilge keels. And this cannot be modelled by strip theory, which is an inviscid potential flow solution. However, for a catamaran, we can consider the roll motion to generate pure vertical motion of the two demi-hulls, and this can be calculated quite accurately with strip theory. In this slide we show some validation of the strip theory compared with some experiments carried out at the University of Southampton in 1995. The experiments consider the demi-hull in isolation, as well as two catamaran configurations with different demi-hull spacings. The experimental results are shown with the curves with symbols, and one can see that there is a little bit of scatter, but generally not much influence of the demi-hull spacing over the results. This indicates that there's very little interaction between the hulls at this speed, which is at a Froude number of 0.53. The strip theory results are the solid black and dashed purple lines, and they represent two slightly different configurations of the strip theory model. And one can see that there's generally good agreement with the experimental results for both heave and pitch. The strip theory method is ideal for calculating the motions of vessels up to moderate fluid number, maybe 0.5, 0.6. What's required is the measurement of a number of stations along the hull and the conformal mapping of these sections to a circle. So the way we do that is in the measure hull form, and can specify the number of stations, so typically 21 to maybe 41 stations is sufficient, and choose the surfaces to be used. You can also specify the number of mapping terms, but in practice this doesn't make a great deal of difference. 3 is typically the value used. So these sections are well mapped by the conformal mapping, partly due to the fact that the waterline is vertical and the centerline is horizontal, which is one of the limitations of the conformal mapping. The 3D radiation diffraction theory available in motions is a boundary element method where panels are fitted to the hull shape and the linearized boundary condition is satisfied on the 3D hull. It can be used for monohulls, catamarans, multihulls, and vessels with complex geometries. The full 6 degrees of freedom are all calculated. The method is limited to 0 speed, and the results are calculated in the frequency domain. And since this is a potential flow solution, viscosity is ignored. The radiation diffraction panel method is more suited to vessels at 0 speed but with more complex geometries. Here we need to mesh the hull with panels instead of using sections. It's only necessary to mesh the underwater part of the vessel, so we select the underwater surfaces and then we can specify various parameters for the mesh. The minimum edge length and the maximum edge length is normally sufficient. Once the analysis has been completed, we can look at the data in various ways, either tabulated data such as this summary table, which includes the significant motions at the various different speeds, headings and wave conditions tested. For instance, I can look at 8 knots, 12 knots and different headings. We can also look at the graph data, for instance REOs at the center of gravity, again at different headings, for instance head seas, beam seas, bow quartering waves, and also the different speeds. We also have a couple of polar plots that can be viewed. The first one shows for a particular motion, so here we're looking at the RMS heave motion. For each angle, the result for different speeds. So basically you can see at the higher speed, 20 knots, we're getting a higher RMS heave, particularly in head seas, whereas in beam seas the heave doesn't vary very much with speed, which is what we'd expect. And in fact in following waves with higher speed shows slightly less significant heave motion. We can choose which parameter we're going to plot here. So we can look at the roll motion. As expected in beam seas or slightly bow quartering is where we get the biggest significant roll motion. We can also look at contour plots, and here we have wave heading and speed and then contour plots for the different motions. So here we're looking at the roll motion, or we can look at the RMS heave motion. So where the contour is most red is where we're getting the highest heave. The decreasing heave here, which sort of is just a different representation of the same data. We'll now look at some of the modelling requirements for stability. One of the main ones is that sections must be closed. What that means is that any section through the hull can have any number of contours, but all these contours must be closed, non-intersecting and non-self-intersecting. You can see a few examples on the right hand side of the screen. The other thing we mustn't forget to do is to set up the frame of reference, in particular the aft and forward perpendicular locations, as this is used to calculate the vessel trim. And if the vessel contains any rooms or tanks which have complex shapes, these may require additional surfaces to be added to the model. So before we load the model into stability for hydrostatic analysis, we need to check that all the sections are formed correctly. And the best way to do this is to turn off any surfaces that are not hull shell. So here all the structure surfaces have been hidden. And then go to the body plan view and turn off the display of everything apart from each section. And then we can step through each section in turn and check that it's okay. So we're allowed any number of closed contours. Here we've got a very small one here right at the stern of the pod. But they're not allowed to self-intersect or intersect one another. Here it looks like a single line, but in fact it's a very narrow section near the trailing edge of the support. So we can step through, use the cursor keys to step through one at a time, and you can check that each section is okay. The other thing we want to check is that the frame of reference is set up correctly, with the forward perpendicular near the bow and the aft perpendicular near the stern, and the datum waterline somewhere that's reasonable. The other thing, because this is a catamaran vessel with twin hulls, we want to check that the vessel type has been set up correctly as a catamaran with the correct demi-hull centerline. So when we first read the model into stability, we're given the choice of the number of sections to use for the model. And typically 50, 100 or maybe 200 if it's a very complicated model could be used. Here we'll use 50. I'll leave the trimming surfaces selected and the precision as selected from the file. So again, we should now check that the sections are formed correctly, and we can do that in the body plan view by choosing View Single Section. Now, as we did before, we can step through each section and check that it's formed correctly. We also do a simple upright hydrostatic analysis of the DWL and look at the sectional area curve. Once the surface model has been generated and the vessel is loaded into stability, this is where we define the rooms, that's tanks, compartments, flooded spaces, etc. Load cases, damage cases, where we can specify the extent of damage, and key points. So something that's of particular interest for multi-hulls, especially catamarans, where bottom raking damage needs to be assessed, is the use of the extent of damage command for the damage case definition. We go to extent of damage. Basically we can specify either a center and a length of damage or the aft and forward extents of damage. We can then specify which side of the vessel, any limits. So here we're going to limit to the port side of the vessel because we're going to limit the starboard damage to 0, which is the center line, but have unlimited damage to port. And we can also specify the top extent of damage. So if I put in, say, 1.2 meters, that will go in just above the double bottom, which the top is at 1 meter. I'll make the aft extent a bit further back, 20 meters. Here you can see the damage case updating for all the compartments that are breached by that extent of damage. In the stability module, there's a wide range of analysis types. These include upright hydrostatics, large angle stability, equilibrium, etc. Each analysis type has a range of parameters that should be set up. These include heel, trim, displacement, and these may be a single value or a range of values. It also includes the fluid method, whether the vessel is intact, damaged, or includes partial flooding. There's also environmental options which include seawater density, grounding, and waveform. We shall now look at the stability criteria which are calculated from the GZ curve in some detail. There are a number of different components including criteria, healing arms, and calculations. We'll have a quick look at the methodology that's used and then look at the customization that's available, including the predefined criteria, the parent criteria, and how the user may customize their own criteria. The stability criteria that are calculated after the large angle stability analysis are defined in this dialog here. Dialog is broken down into 3 areas. One with a tree with all the different criteria that may be used, and on the right we have a table with the details of the selected criterion, For instance, here we can select different criteria and the table updates, and below that a small section with help on the particular criterion that has been selected. So at the top of the tree in bold we have a list of all the parent criteria, calculations and healing arms that may be used. Below that we have a list of predefined criteria which are all derived from one or other of the parent criteria. When you are evaluating criteria, you may use either the predefined criteria, modifying if necessary, or you can create your own set of criteria from the available parent criteria, healing arms and calculations. As you can see, there is quite a wide range of different healing arms and parent criteria. So now I'd like to briefly show you how you can generate your own criteria sets. So the first thing is to add a new group. Should be, you can give it any name. And I'm going to add some criteria that I'm going to use for my high-speed catamaran based on the HSC Multihull code. So now I need to locate the criterion that I need, which is the GZ area between limits for the multi-hull. I can just drag that into my folder and give it a name. So now I can edit the details of the criterion. So I want the GZ area from 0 degrees to 30 degrees or the lesser of the angle of maximum GZ for first down flooding. And this needs to be greater than this value here, 0.055 meter radians. The second criterion is the HLT criterion, which is the area between the GZ and healing arm curves from equilibrium with the healing arm to the lesser of 15 degrees above equilibrium or down flooding. And we need to look at two healing arms, wind plus gust plus passenger crowding, and wind plus gust plus high speed turning. So the first step is to add the healing arms. So we want the wind, we want turning, and we want passenger crowding. Then we need to find our criterion, which is a multiple healing arm criteria using cross-referenced healing arms. And it's the GZ area between limits criterion. And again, you can just drag that down. So you can give it a name. And again, give the details. So the first thing to do is to select the healing arms. So we want the wind healing arm, the turning healing arm, and the passenger crowding healing arm. Now these healing arms here are only the ones that are in this folder here, so they have to be in the same folder. So we want the area from the angle of equilibrium with the healing arm to 15 degrees above the angle of healing. Sorry, the angle of equilibrium with the healing arm, or the first down flooding. We can leave angle of vanishing stability. And then we want to consider following combinations of healing arms, so wind plus turning and wind plus passenger crowding. Now it remains to specify the healing arms, so we can specify the wind pressure, which is 500 pascals, the area centroid of any additional area, so maybe for this model 20 meters. And here we can either specify the total windage area or an additional area. If we specify additional area, then the area that's modelled with the vessel will be taken into account. So we can put something like 500 meters squared. And then for this criterion, we should use half the mean draft as the height to the lateral resistance and the gust ratio of 1.5. For turning, we can specify the vessel's speed, so say 40 knots, radius of turn either as a percentage of the waterline length or as a radius, so we can maybe put 200 meters in here, and again we should use the kg minus half draft. We also have the option of specifying n, which is the shape of the healing arm curve. And for these IMO criteria, the healing arm is constant with heel angle, so we have a cosine power of 0. And finally, the passenger crowding. So maybe 1,000 passengers, passenger mass, say 90 kilos, and all on one demi-hull, I think is 15 meters. Now if we want to evaluate these criteria, we just put a tick in each one. So we want the HLT criterion to be evaluated, which will in turn evaluate these healing arms, and we want the area criterion to be evaluated. So we can click recalculate and close. And here is our GZ curve with the different wind healing arms put on, and the results here. So any new criteria that you create will automatically be saved in the criteria library for stability. But if you wish to save some specific criteria with a specific vessel model, you can do that also. So if I open the dialog, I can go to my selected criteria, right click on the branch and say save branch as. And then I can specify a name and save it with my project.